Can you see my slide page?
Yes, sir.
Okay. I'm going to talk about the grading in this course. You probably taken all three tests now. The test 4 is optional. If you are happy with first 3 tests, then you don't have to take the 4th test. So I normally drop the lowest test score. If you have another lower score, you have to take the test 4. So I can keep whatever you earn on test 4 as if it is not the lowest. So I normally drop 1 test score out of 4. You already taken 3. If you are happy with them, then test 4 will be your lowest test score. The test 4 should be taken on between November 15th and 21st. It's online. I let you do it 4 attempts, 3 attempts. You can try once, twice, 3rd time, highest test score will be kept for the test 4. The final exam is open up on November 15th. Preferably you need to take it before November 28th so that I can give you a final grade. Final exam also allows 3 attempts. So you can do 3 times and keep the highest test score for the final. Final is covering only chapter 1 and 6. First 3 tests. So therefore, there's no new material in there. So you already gone over chapter 1 and 6. If you need more points, there's a bonus paper. You need to go to the webpage and select a topic and submit a paper that I can grade so that you will get extra points if you need them. All right. Do you have any questions about testing and about?
No, sir.
All right. I'm going to go over chapter 7 material and 8 material. You need to do quizzes on chapter 7 and 8. They are unlimited attempts. So at least you get exposed to the material. So that's the idea. Okay. All right. I'm going to go to chapter 7. Chapter 7 is on reaction rates and chemical equilibrium. These are 2 separate topics. Reaction rates deal with how fast reactions are complete. Some reaction takes slower times, short times. Some reaction take days. Some will take months, years. So we need to improve products or complete reaction in reasonable time. Reaction rates deals with that. Equilibrium is another thing we deal with, where chemical reactions take place both ways. Reactants go to products, goes back to reactants. Reactants and products are in equilibrium. We're going to talk about that. It's important to understand acid-base chemistry, chemical equilibrium. So we're going to, in chapter 7, we're going to talk about measuring reaction rates, how you measure rate of a reaction. Rate of a reaction is dependent on molecular collisions. So we're going to look into that. The collisions are important to reaction to take place. But collision should have enough energy. Enough energy means activation energy to complete the reaction. Reactants to go to products. Activation energy is important for reaction rate. Higher activation energy means slower reaction. Lower activation energy means faster reaction. So rate of a chemical reaction, we consider all these factors. Equilibrium is the second topic. Equilibrium reactions are where reactants go both ways. Reactants goes to products, products react back to produce reactants. There's an equilibrium, same concentration for reactants and products. They are coexisting. Not all the reactants are converted to products. So that deals with equilibrium. We define a constant called equilibrium constant to tell you, to figure out how much products and how much reactants remain in the equilibrium. Equilibrium constant is a value that you can use to predict whether there are more products or less products. We need to change the equilibrium. We need to complete reactions. There are few ways that we can change the equilibrium so that we can get more products and at lower temperature. Le Chatelet principle deals with equilibrium condition, how we manipulate equilibrium to get what we wanted. We're going to look at the end of this chapter. I am not going to talk about these details about instructional objective, since it need going over the material. The first topic we deal with is reaction rates. The area of chemistry that deals with chemical reaction rates is called chemical kinetics. The study of rate of chemical reaction is chemical kinetics. If you consider a reaction that takes place as shown below, chloromethane, first reactant, and the second reactant, iodide ion. Iodine ion replaces the chlorine in the chloromethane, and chloride ion is produced. Iodomethane is produced. It's kind of single displacement reaction. This is one of the reactions we are going to look at. To find out the rate of a reaction, we need to measure concentration of iodomethane, that's the product, or the reactants. We can measure reaction rate using either reactants or products. Either products or reactant concentration. You have to observe them at periodic time intervals, every 10 minutes or 10 seconds. So we observe the concentration and measure the reaction rate. The rate of a chemical reaction for the reaction we looked at in the previous slides. The rate of a reaction is decreasing. Concentration of the reactants decrease during the reaction. Concentration of products increase. It depends on the product or reactant. However, the time interval is same. So you can say that chloromethane concentration decrease as the reaction goes, iodomethane, the product, increase concentration. For example, iodomethane concentration might increase from 0 to 0.2. That's the change in concentration from 0 to 0.12 every 30 minutes. So reaction rate over this period is change in concentration of iodomethane divided by the time it took, 30 minutes, you get 0.0040 mole liter per minute. That's the rate of reaction. You can also calculate the rate of reaction using chloromethane. That will be, concentration will be decreasing. So it will get a negative rate. But anyway, rate is, regardless of increase or decrease, they are equal when you use either chloromethane or iodomethane. The units is rate. The units of rate of reaction is mole per liter. That is the concentration units divided by time per minute. So if you look at a reaction that A is the reactant, change into B with respect to time. If you look at the graph, on the y-axis, concentration of the B is shown. So we are looking at the products in this diagram. The product concentration is 0 at the beginning, right here. Right here, product concentration of 0. It increases as time goes on. The rate of the reaction is shown by the slope to the graph. At the beginning, rate is higher. As the time goes on, it flattens out, rate becomes 0. You start with a higher rate, positive rate, then it becomes negative. So rate of reaction decrease as the time goes by because less reactants are there. So therefore, rate of reaction depends on the concentration of the reactants. What factors affect the rate of a reaction? Let's look at that. Rate of reaction are affected by following factors. Nature of the reactants. If they are reactive material, they undergo fast reaction. Unreactive, slow reaction. Concentration of the reactants. Rate also affected by, in the previous graph, you saw that rate was higher at the beginning. The rate of concentration of reactants are higher at the beginning, gets lower as the reaction goes on. Rate also depends on molecular collision. Molecules must collide for reaction to turn into products. This collision should produce enough energy to break the reactant molecules to products, convert reactant molecule to product. This energy that collision must provide is called activation energy. Temperature is dependent on, directly proportional to kinetic energy. Therefore, higher the temperature, more activation energy. Collision with more activation energy is produced. Therefore, temperature increases the reaction rate. Catalysts also increase the rate of a reaction without being consumed. That's the definition of a catalyst. On the following screen, we examine these factors one at a time, starting with nature of reactants. Nature. In general, reaction between molecules in gas phase are very fast. They have lower activation energy. Gas phase have activation energies are lower. In aqueous solution, ionic compounds also react very fast. Their activation energy is low, but higher than gas phase reaction, molecules in gas phase. Ionic compounds have slower rates, but they still have lower activation energy. The covalent compounds, when dissolved in water or another solvent, are slower. The activation energies are higher. Therefore, activation energy decide how fast. Basically, activation energy is the first thing that will tell you whether the reaction is fast or slow. Concentration, higher the concentration of reactants, higher the rate. In most cases, reaction rate increase with the concentration of either or both reactants increase concentration. Sometimes rate depend on one of the reactants. So that's why we say either both or one. For many reactions, there is direct relationship between concentration of a reaction rate. Again, taking the example, A is going to B, reactant A going to B. This is the rate of the reaction, which depend on to the power 1. There's a 1 in here. Exponent is 1. So it's called the first order reaction. Rate depends directly on the concentration, 1 to 1. If the concentration increase, rate increase. But there are reactions which are called second order. The exponent is 2. If the concentration is double, rate quadruple. Quadruple means 4 times. Because if you double something, it becomes 4 times, 2 to the power 2. So they are fast, they affect second order reaction, concentration have more effect on the rate than the first order concentration in the rate. Now we're going to talk about molecular collisions. Collisions are required for reaction to take place. They must collide. It is possible to calculate how many collisions will take place, how many collisions will take place between A and B. You can calculate this one. Such calculation indicate rate at which A and B collide is far greater than rate at which they react. There are many collisions, calculations show, but not all collisions lead to products. Therefore, there are effective collisions. The conclusion is that most collisions do not result in a reaction. When you mix up reactants in a container, they collide many times, but most of the collision doesn't result in products. Collision that result in reaction is called effective collision. That's kind of pretty straightforward. Only fraction of collisions lead to. Now what decide the effective collision? The collision should have activation energy. The two main reasons why some collisions are effective is they have enough activation energy, and their orientation of the collision orientation of the reactor are proper. Therefore, their orientation also has an effect on effective collision. So therefore, effective collision are decided by activation energy and relative orientation of colliding particles. Let's look into these two. Molecular collision on activation energy. Activation energy is the minimum energy required for a reaction to take place. The collisions should have the minimum energy, which we call activation energy, to get converted to products. In most reactions, one or more covalent bond must be broken, and energy is required this to happen. Activation energy provides energy to reorganize the colliding particles to products. So some bonds need to be broken. So that's why the activation energy is important. The energy comes from this energy to reorder bonds, to break some bonds, come from the collision energy produced in the collision. If the collision energy is large, there is sufficient energy to break the necessary bond and produce the reactants to get converted to products. If the collision energy is too small, no reaction takes place. If there's not enough energy to transform reactants to product, nothing. These are not effective collisions. They are lower energy than activation energy. Now we're going to look at the orientation effect. We talked about that collision must produce enough activation energy. Also, the collision should have certain orientation at the time of a collision. The colliding particles may be properly oriented for bond breaking and bond making. We look at an example, water and HCl. HCl produce a proton, and I'm going to show the reaction here. This is the two reactants. This is the product. In this case, a proton is transferred from chlorine to oxygen here. So therefore, orientation is important. If the collision takes place in the B situation, if the hydrogen is away from oxygen, even if they collide, they don't have proper orientation to transfer, like in this case. In the diagram A, hydrogen is with the proper orientation. So therefore, some collisions, even though they have activation energy, the orientation is not correct. So collision will not be effective. Now, energy changes in chemical reactions are important. You can show all these energy changes in an energy diagram. Let's consider reaction between hydrogen and nitrogen. This is 3 hydrogen molecules plus nitrogen molecule going into 2 ammonia molecules. So I have drawn the Lewis structures for this. There are three hydrogen bond, 3 nitrogen bond in triple bond, hydrogen, and 3 NH bonds. There's a 1, 2, 3. So 6 bonds are broken in the products, in the reactants. This side 6 bonds are broken. This side 6 new bonds are formed, NH bonds. So in this process, to break bonds, you need energy. When bonds are formed, you release energy. You need energy means endothermic. You release energy means exothermic. So this is the total reaction, depend on how much energy required to break 6 bonds on the reactant side and how much energy is released, forming 6 NH bonds on the product side. In this reaction, 6 covalent bonds are broken and 6 new bonds are formed. In this calculation, triple bond is counted as 3 bonds. Breaking bonds requires energy and forming bonds release energy. In this reaction, energy release in making the 6 new bonds is greater than the energy required to break the 6 bonds. Therefore, reaction is exothermic. This reaction is exothermic. It's more energy is released, forming the products than energy required to break the bonds in the reactant. Therefore, exothermic reaction. This energy change is dependent on bond breaking in the reactants and bond forming the products. So you can show some of this in an energy let's see. I may have another diagram. This is the previous reaction with the proper orientation here. They collide this way. And activated complexes. Transition state is where these two molecules, two reactants, coming together to break a bond here and make a bond here. So there's a new bond is formed. All bond is broken. Now the bond broken have less energy than bonds formed. This bond formation release more energy. Therefore, is exothermic. So this bond broken takes up less energy. Therefore, is overall reaction is releasing energy. This height right here. This is exothermic reaction. Now, in this diagram, the activated complex or transition state is at the top of the activation energy curve here. This is where the transformation from reactants to products take place. Reactants go to the transition state and then they turn into enough activation energy is provided, orientation factors are good, then reactants go into products. It always goes through reactants go to transition state. Transition state is the state where the reactants are products are interacting with each other, bonds are formed, broken, and transition state is if it doesn't have enough activation and it goes back to products, reactants. If it has greater than activation energy, it turn into reactants, turn into products. So these diagrams are very useful in showing the energy changes during the chemical reaction. So this is a generic diagram, but this is different than the previous one. Previous one, you had this. This is exothermic. In this case, the products have higher energy than reactants. Therefore, energy should be absorbed. It tells you that to break the bonds in the reactants take up more energy than energy released in the forming the reactants. This is exothermic reaction, This is endothermic. So you can see that activation energy is there. Transition state is the maximum of an energy diagram where the activation energy is given to colliding reactants to form a transition state. For example, CHCl3 iodomethane bond is partially formed, and we looked into that. Cl bond is partially broken. This is the diagram. Now, this also helps this activated complex to have the proper orientation. If the iodine atom hit from this side, reaction is not going to take place. You have to hit the carbon from this side to kick out chloride. Okay, so this is the activated complex. The Cl bond is partially broken in the transition state, and this is partially broken, Cl bond. Carbon iodine bond is partially formed. When it goes to products, this iodine separate out and iodomethane is formed. Now we're going to look at the effect of temperature on reaction rates. Temperature is virtually always increase the rate of a reaction. It's because temperature is related to kinetic energy of the colliding particle. Approximately for every 10-degree increase in temperature, a reaction rate doubles. When temperature increases, molecules move faster. They have more kinetic energy, which means they collide more frequently. When you move things faster, they collide faster. Also, they have collision with higher energy, and they increase. Higher energy means above activation energy. They contribute to higher reaction rate. Therefore, importantly, fraction of molecule with energy equal to or greater than the activation energy also increase. This is the more important factor responsible for increasing temperature increase. There's a diagram here. This is high temperature. T1 is high temperature. T1 is lower temperature. T2 is higher temperature. That's given here. T2 is higher. As the temperature increase, normally if you start with low temperature, the distribution of the at higher temperature, kinetic energy distribute over large kinetic energy. So this is the higher temperature has more distribution extending to higher kinetic energy range. Therefore, fraction, this is only for T1. This combined area is T2. Therefore, there's more molecules at higher temperature with higher kinetic energy to produce more activated complexes with enough activation energy. So that's how we describe how the temperature affects the molecular activation and then increasing molecular velocities at two different temperatures. The effect of the catalyst on rate. Catalysts are defined as substances that increase the rate of a reaction without being consumed. They don't participate in the reaction. They only provide a surface or substrate. Energy diagram of catalyzed reaction. If you look at this diagram, this is uncatalyzed reaction. And uncatalyzed means no catalyst. Activation energy higher. This is for catalyzed reaction. Therefore, activation energy is lower. Because catalysts provide a stage for reactants to come together, they increase the probability of reactants to combine without having to undergo high energy molecular collisions. Therefore, activation energy is lowered by adding a catalyst to a particular reaction. Therefore, reaction rate is increase rate. Lower activation energy means faster rate. What makes a catalyst effective? One way catalyst can affect the rate of a reaction is to provide a surface on which reactants can meet. For reaction between formaldehyde and hydrogen, which is an exothermic reaction, this diagram, exothermic, would have one like that. With the catalyst, it lowers the activation energy. Therefore, it takes place faster. Platinum is the catalyst. If two reagents, formaldehyde and hydrogen, are mixed, there's no visible reaction even over a long period of time. But when they mix and shaken with finely divided transition metal catalysts such as palladium, platinum, nickel, we use nickel here. Nickel is inexpensive, so cheaper. Reaction takes place readily at room temperature. So you don't even have to heat the mixture. Shake the reactants together, reaction take place. Catalysts help to lower the activation energy and increase the rate of reaction. Now we're done with reaction rates. So I'm going to cover some of the other material, some of the new material in reversible equilibrium reaction in the next class. There's a recording from my previous class. If you wanted to listen to that, you can do that too. Okay? So we're going to meet on Thursday, finish the chapter 7. All right?